Welcome back, guys!
Okay, so for halogenalkanes, we're going to look at the reactions now. We have learned in the last lesson that halogenalkanes react via nucleophilic sub, and we have 4 reactions here, 5.1 to 5.4. We're going to be focusing on 5.1, 5.2, and 5.3 first. I'm going to remind you again, the carbon that is directly attached to the electronegative halogen, it is electron deficient. So in 5.1 to 5.3, we have 3 different types of nucleophiles here. We have your OH minus nucleophile, we have your CN minus nucleophile, and we have your NH₃ nucleophile. Now, Mr. Leong, can you bring me through reaction 5.1, please?
Right, so reaction 5.1 to 5.3 are all nucleophilic sub. That's where you see a nucleophile coming in to attack the halogenoalkane. The reason why is because your X is electronegative, causing the C to be electron deficient. So as a result, you notice that the attack is going to happen. So the OH attacks the electron deficient carbon, causing the CX bond to break. So at the end of the day, you'll end up with an alcohol. Now, in order to introduce the OH minus over here, we will need to use a strong base performed under the aqueous medium. And this reaction, sometimes we call this alkaline hydrolysis, right? Now, at this point of time, let's try to go through question 8. So you can pause this video, help me to try out part A and part B, and the moment you're done with it, you can continue with the video.
Okay guys, welcome back. So if you look at question AA, you will realize that there are 2 halogens bonded to the same carbon. So when you do a nucleophilic sub, the OH minus nucleophile, you'll sub away both of the halogens away. Now this will give you 2 hydroxyl groups bonded to the same carbon. This is what we call a geminal diol, 2 hydroxyl groups, diol. Okay. Now, geminal diols are never stable, so it will spontaneously eliminate water. This is what we call dehydration. So do this with me. We're going to circle a water molecule, OH, H, water. We're going to remove it completely, delete it away, and we're going to form a double bond with the carbon and the oxygen here. Okay. Now, this is what we call an aldehyde functional group. This is C double bond O attached to a hydrogen. So one more time, the CO functional group where the carbon is attached to a hydrogen. This is what we call an aldehyde. So for 8B, something similar. So again, we have 3 halogens attached to the same carbon. So when you do nucleophilic sub, all right, you have 3 hydroxyl groups bonded to the same carbon. Mr. Long, what do you call this?
This is going to be a geminal triol now.
Okay. Now again, it is unstable, right?
That's right.
So it will spontaneously dehydrate, remove water again. OH, H, delete it off, and again form a double bond between the carbon and the oxygen, and we see this COOH functional group. And what do we call this, Mr. Leong?
So this is a carboxylic acid.
Yes, and that's it. So in general, guys, any molecule with 2 or 3 hydroxyl groups on the same carbon is what we call a geminal alcohol. If it's 2 hydroxyl groups, diol, 3 hydroxyl groups, triol, and it will undergo spontaneous dehydration, elimination of water. Okay.
Now, reaction 5.2 is another nucleophilic sub-reaction, but in this case, my nucleophile is going to be known as this CN minus. What is this CN minus called, Mr. Tim?
Cyanide, right?
Cyanide. Yeah. So this is cyanide is poisonous, right?
Oh, it is.
Yes. So in this case, we are going to see that the lone pair is now going to be occurring on the C, and it's going to perform a nucleophilic attack because this X is electronegative, causing the C to be electrodeficient. So the attack is going to be on the carbon, causing the CX bond to break. Right? At the end of the day, you're going to see the CN being introduced into the organic compound, where it is the C that is bonded to the organic molecule. So in this case, what kind of functional group is this known as?
Nitrile.
A nitrile, right? So just to remind you again, this is going to be a triple bond N in between them. Right? Now, who is going to introduce your CN minus? The reagent over here has to be ethanolic NaCN or KCN, and the ethanolic is actually going to be my solvent. Right? Now, in total, we notice that this reaction itself increases the number of carbon by 1, and that is why we call this a step-up reaction.
Okay, so in reaction 5.3, it's going to be something similar, but instead of a cyanide or a hydroxyl nucleophile, we're going to use an ammonia nucleophile, but the idea is to do the same thing. Focus on the lone pair, on the nitrogen, it is nucleophilic. It's going to attack the electrophilic carbon, once again, break that CX bond, release that X minus, and your product is a primary amine. Now, before we move on, Mr. Leong, can you tell me why do we have to heat it in a sealed tube? Right.
So ammonia that you used earlier is actually a gas at room temperature, right? So if you heat it, it is still a gas, but we don't want the gas to escape into the atmosphere.
Right.
So you must do it in the sealed tube to contain the ammonia.
I understand. Okay. So Mr. Leong, I want to have a thought experiment with you. Imagine if there's a lot of Rx molecules floating around in excess, so excess Rx. Now, think about this with me. I have excess Rx. I have two nucleophiles present. I have an amine nucleophile with that lone pair there, and an ammonia nucleophile, which is a stronger nucleophile, Mr. Leong.
Right. So if I compare between ammonia and the amine, you notice that the amine has an additional alkyl group. And what kind of effect does my alkyl group exert?
Alkyl group's electron donating group.
Exactly.
Yeah.
So it's electron donating,
Right.
which means that it's going to push electron density towards the N, making N a stronger nucleophile.
Okay, so if the primary amine is a stronger nucleophile, then the competition will be between the stronger nucleophile and the weaker nucleophile, and of course, the strong guy wins. He attacks the R, breaks the Rx bond. Now what happens is this. If you flip to this page, you will realize that when the product is a stronger nucleophile than the ammonia, it's going to keep attacking. It attacks once, becomes a secondary amine, it will attack again, right? And again, and all the way until quaternary ammonium salt. Now, Mr. Long, do we want that?
I doubt so.
No, right? Because we want to stop at the primary amine. We want to stop there. So, Mr. Long, how do we combat this issue? We can't use excess Rx, we have to.
Instead, we have to use excess ammonia.
Yes.
And this is exactly the reason why at the start, you notice that the reagent requires you to use excess ammonia. This is to prevent multiple substitution.
Exactly.
So you only end up with the primary amine. Okay, the last reaction that we're looking at is no longer a nucleophilic subreaction. Now, this reaction itself, we are going to start to remove a X together with a H that is just beside it. Now, when I say beside, I'm referring to these two attaching to carbons that are adjacent. Now, as a result, you're going to form a double bond in between them. So, Mr. Tim, what kind of functional group is this?
Well, it's an CC double bond, so
Right.
it's an alkene functional group.
That's right.
Yeah.
And in this case, what type of reaction are we undergoing?
Well, we just eliminated a HX molecule, so it's called an elimination.
That's right. So this is an elimination reaction, right? Now, bear in mind that this reaction, right, the H that you're removing has to be on adjacent carbon from the X. So in the event that there is no adjacent hydrogen attached to it, you notice that elimination cannot happen, right? So for the example over here, there are no H's beside the BR. That's why there is no elimination going on, right? So bear in mind that this H cannot be removed because these two are actually belonging to the same carbon, right? Now, let's take a look at example 10 below. So the BR, remember, has always to get eliminated with an adjacent H. So for this particular halogenoalkane itself, there are two options. You can either eliminate together with the left H, or it can be eliminated with the right H. That will end up with two different products. So Mr. Tim, do you think that these two products, these two alkenes that you get, will be present in equal amounts?
Unlikely, right? Unlikely. So we have to apply this rule called César's rule. So can you guys box up your alkene functional group with me? Mr. Leong, how many alkyl groups do you see directly attached to that CC double bond?
So if I zoom in into the box itself, there's just only one, which I see, there's going to be two, one on the left and one on the right hand side.
Yeah, and this is what we call a di, meaning two, substituted alkene. Now if you look at the one on the right, this alkene double bond, how many R groups do you see directly attached?
So if I look at the box in itself, there's only just one of them. Yep. So that's on the left hand side over here, you can see.
Exactly. And this is what we call a mono substituted alkene. Now according to César, who is dead, but César says this: the more substituted alkene will always be your major product. Okay? Now, so the reagents and conditions for this is actually ethanolic KOH. Mr. Leong, do you want to bring us through this?
Yes.
Yeah?
The last thing that I want to talk about this reaction is the reagents and conditions. So if I take a look here, it's going to be ethanolic KOH and NaOH. Now this is going to be different from our aqueous KOH and NaOH because the solvent you're using is different. For aqueous, the solvent is
water.
And in this case, we are using
ethanol, right?
Ethanol or alcohol, right? Now what is the impact of using alcohol as a solvent? We'll see it in the mechanism below. Now, usually, right, this OH over here would like to attack this particular carbon. The reason why is because this carbon is electron deficient. So what's going to happen now if you use an alcoholic solvent is that this alcohol is a huge molecule. It is going to start to obstruct my halogenoalkane a little bit more. So the OH, instead of attacking this green carbon, right, it is now going to attack the nearest small atom, which is a hydrogen atom. Now, in this case, what's going to happen is that it's going to trigger a new set of mechanism, which will eventually end up with an alkene. So if I look at this particular reaction itself, Mr. Tim, OH minus is going to grab a H plus over here.
Right.
What kind of role is it acting?
A base.
A base, right? What kind of base?
it's a Bronsted base, right? If you're accepting a proton, that's a Bronsted base.
That's right.
Yeah.
And what kind of reaction are you expecting to see?
So, acid-base reaction.
That's right.
Yeah.
So, Mr. Tim, can you help me to conclude this together with the aqueous NaOH?
Yeah, so we have quite a nice summary here that we have. So if I use alcoholic NaOH, Mr. Leong, can I say that I get 100% alkenes?
Unfortunately, organic reactions are never 100%.
Right, never 100%. So your alkene will be the major product, but if you use aqueous NaOH, water, as your solvent, you realize that you get a nucleophilic substituted product as the major. Okay? And that's it.
Oh, wow, Mr. Tim. That's a new dance. Are you trying to start a new fad on TikTok?
No, this is a step-up dance, Mr. Leong.
The only step up that I know is a step-up reaction. That is found in reaction 5.2, as you can see on the notes over here. What happens is that we start off with a halogenoalkane, and we're going to use a cyanide ion to perform a nucleophilic subreaction. And as a result, we're going to get a new functional group known as a nitrile functional group.
Okay.
Right? Shall we take a look at the reactions of the nitriles? Yeah,
so we have 3 reactions here. I'm going to walk you through reaction 5.5, and it's quite simple. What you're doing here is that if you look at your product and you look at your reactant, you're just adding in 4 hydrogens. So this is a very simple reduction reaction, gaining of hydrogen. So do this with me, guys. We're going to expose that nitrile functional group, okay? And what we're going to do is we're going to put in hydrogen atoms. And every time we do that, we remove 1 pi bond. Goodbye. Put them in. There is still another pi bond. Remove that pi bond again. Put in 2 more H atoms. And we have this here, right? So this is what we call a primary amine, all right? And your reagents and conditions for this, you could either use lithium aluminum hydride in dry ether, or you could use hydrogen with nickel, all right?
Now the next reaction that we're looking at is known as a hydrolysis reaction. The name can be broken down into 2 parts, hydro and lysis, where you take the water to break it down, right? So specifically in terms of the nitrile, let's expose the triple bond again. So what's going to happen in the hydrolysis reaction is that the triple bond is going to break entirely. The C is going to turn into COOH, right? The O's and the H's will come from the water that was being broken down. The N would now change into NH₃ over here.
Okay.
Right?
Okay.
Now, this particular hydrolysis reaction is going to be conducted in the presence of a strong acid.
Right.
So this means that it's going to be in an acidic medium. So Mr. Tim, can you tell me what additional reaction is going to happen?
Well, if it's under acidic conditions, it's going to protonate the base, which is ammonia.
So this NH₃, which is a base, is going to be accepting 1 more H+, and you're going to end up with ammonium chloride.
Makes sense.
Right? Now, we're going to take a look at 5.7, which is also another hydrolysis reaction, except that now we're going to perform this under alkaline medium. Right? Okay. So let's repeat the steps again. Expose the C triple bond N, and hydrolysis is going to entirely cleave my triple bond. The C is going to give me COOH, whereas the N is going to give me NH₃. Right? Now, Mr. Tim, can you tell me in the presence of a base, who else is going to additionally react?
Well, base reacts with acid, so the COOH will react with the base.
Right. So it is going to add a OH minus, and you're going to achieve a
CO minus carboxylate salt.
That's right.
Yeah.
All right. So, Mr. Tim, now that we've finished up the step-up reactions, I understand that you've been in a relationship for quite a period of time. So when are you going to step up your game?
My gosh.